here. Okay, so after your project is done, we are getting back to partial differential equations. And previously, we have learned the finite difference method, right? We have learned the finite difference method for solving the kind of equations that looks like the derivative of u with respect to time plus a speed of advection. Now we are able to start putting these terms into their physical meanings, because we have already seen a lot of solutions, and we can now think about what they are. So this term, a first order derivative in space, when you write it in an equation that also has a first order derivative in time, is usually called the advection. So it is basically the role of this term is to move the solution around with a certain speed, and the particularly a is the advection speed or wave speed. Advection speed or wave speed. And the second derivative term is called diffusion. Okay, and the k is the diffusion coefficient. Usually it's kappa. Diffusion. Don't remember. Coefficient. All right. So the role of this term is to basically make the solution less oscillatory, removes all the angles and sharp features, make it smoother, and eventually a constant. All right. Later, we're going to be looking into a little bit more about these terms, do more rigorous analysis on this. But let's we already know the behavior of these terms in at least a qualitative manner. Okay. And we also studied how do we approximate these derivatives. First, the time term we're going to be approximated later after we approximate the spatial derivatives. Because we know once the spatial derivatives are approximated, we get a coupled ordinary differential equation, and we can use forward Euler, backward Euler, Runge-Kutta schemes, whatever we have done in ODEs to discretize the time derivative. So in PDEs, we only really focus on the spatial derivatives. And the way we have been discretizing the spatial, first order spatial discretization derivative has been 3 different methods, and we have seen how they are used in different scenarios. We can discretize it as un plus 1 minus un divided by delta x. So that's a right biased approximation. Right, it's biased towards the right-hand side of the grid point. So because we are trying to approximate the grid point at n, we can also approximate it using a left biased approximation, taking the grid point in the middle and the grid point on the left. We can also take a centered approach, so using both un plus 1 and un minus 1, and here we have to divide by 2 delta x. So this is a centered approximation. Right. Usually you also see people talk about schemes. That's basically what approximation is used here. You can say this is a right biased scheme, a left biased scheme, or central scheme, right, or centered scheme. Okay, and the reason we looked into all of that is because they have different scenario in which they are appropriate. Okay, so the centered approximation is second order, but it turns out the result is very oscillatory, right? And we have done the stability analysis, and all the eigenvalues after we have approximated it is where? Do you remember? Yeah, it's actually exactly on the imaginary axis. So let me actually draw the stability here. So let's say if this is real of lambda, this is imaginary of lambda. So if we write the scheme as a matrix form, that means we are going to be writing the approximated derivative at every grid point as a vector, as a column vector. And also write the the solution at every grid point as another vector. Then the approximate derivative is equal to a matrix times the solution. And then we compute the eigenvalues of the matrix. And for a centered approximation, all the eigenvalues lies on the imaginary axis. So this is centered. Okay, and the upper and lower bound, I believe, is a 1 over delta x times I, of course, and minus 1 over delta x times I. Okay. Now for the right biased approximation. Well, I always forget which side of the imaginary axis does it lie, but like you can really figure that out by thinking about what kind of advection speed it is stable for. Okay, a biased scheme is always stable if it's an upwinded scheme. So if it's an upwinded scheme, when we are looking towards the right, when we are looking towards the right using a right biased approximation, and the wind is coming from the right, which means it is blowing the solution towards the left, right? And we know A has to be negative for this to happen, right? A has to be negative for the solution to move towards the left, which means the wind comes from the right. Okay, for a negative A, if we move the whole derivative to the right hand side, it's actually a plus du dx, right? And for that to be stable, my right biased approximation has to have eigenvalues lying over here, right? So this is right biased scheme, and it's centered at minus 1 over delta x. All right, so a corresponding left biased scheme would be stable for positive A's, where the wind is coming from the left, is blowing the solution towards the right, right? So this would be a left centered scheme, and the center of the circle would be 1 over delta x.